Welcome to lesson 1.2. Today we're going to do more on limits, more on continuity, and introduce you to something called the intermediate value theorem, which always seems to be on the AP exam, so be aware. Now, we looked at limit questions last day with piecewise functions and those that could be evaluated by direct substitution. Now, what happens today when we do questions like these rational expressions? And let's see what happens when we actually try to do this by direct substitution. Look at example number 1. Limit as x approaches 0 of x over x plus 1. So if I plugged in 0 to the numerator, I get 0. If I plug in 0 into the denominator, I get 0. And then you're like, what's 0 divided by 0? Oh, please don't say 1. No. Actually, 0 over 0 is what we call an indeterminate form. We don't really know how to deal with it. And so what we need to do is use algebraic techniques to change the form of this limit. Now, for those of you that did your pre-calculus 12 course, hopefully you recognize that this is a rational function with a common factor in the denominator. Does that produce an asymptote or did you think of the word point of discontinuity? If you thought about that, you are correct. So remember here, what we need to do with the algebraic techniques is ultimately we need to simplify this expression. And once we've simplified it by dividing out both x's, what we now have is this simplified form. And now if we plug in the limit as x approaches to 0, what you will find is that the answer here, if I plug in 0, equals to 1. Now remember, if you were to think about what this graph looked like in pre-calc 12, you had to graph this out. 1 over x plus 1 is one of those rational functions with asymptote at -1, and then the curve that looks like this. Whee! But notice at 0 what particular thing happens. If you remember from your pre-calculus 12 days, there was a hole or a point of discontinuity. So really, at that hole was the value of x equals 0, and the y value was actually 1. So in essence here, what I'm saying is the limit as x approaches to 0 approaches that hole, and that hole has a coordinate value of 0, 1. Remember this stuff? So now whenever you try to do direct substitution, if you always get 0 over 0, you know you have to do some algebraic technique. Factoring is one of them. Okay, so see if you can try examples 2 and 3 on your own. Go for it. Yes, you get 0 over 0 again. So therefore, an indeterminate form. We will just do some nice factoring. Beautiful things divide out. And then I can substitute into the simplified form, and I get the answer 1/4. So for this one, the whole, if you're curious, was at 2, 1/4. Yes. It's funny because all these values here, right? The 2 that I chose, the 0 before, those are the non-permissible values. Because if you look at the denominator, that's where it equals to 0. Same thing with number 3. So, hopefully you remember how to factor a cubic. If you don't, oh no, but that's okay. You should do some long division. So factoring a cubic. Don't know if you remember long division. And if you don't remember long division, if you memorize the formula to factor this difference of cubes, that's fine. You can do that as well. Those of you who love, oops, what am I doing? I meant to write down x cubed minus 1. Now, by the way, I like to actually go ahead and fill in the remaining missing terms with 0 with the coefficient. So let's go ahead and divide. So x goes in x cubed, x squared times x minus 1 gives you x cubed minus x squared. We'll subtract x cubed minus x cubed is 0. 0x squared, this is why I do that now, so I can line things up. 0x squared, take away negative x squared is positive x squared. We'll bring the 0x down. X times what gives you x squared? There's another term of x. This gives you x squared minus x. We'll subtract once again. The x squared becomes 0. Perfect. 0 minus negative x becomes positive x. or just x, we'll bring down the 1. That's perfect because now we have a factor of 1. X minus 1, we subtract, lo and behold, 0. Yay! So ultimately here, what we just did was we divided x cubed minus 1 by x minus 1. And we have here the quotient of x squared plus x plus 1. That now becomes my new numerator. And then now look at this. The factor of x minus 1 divides out. Perfect. And then now when I plug this in, I get 1 plus 1 plus 1, which is 3. And in this case, the whole was actually at 1 comma 3. All right. So let's take a look at number 4. Interesting one here. Ooh, square roots. You're like, I don't know what to do with square roots. Well, there's actually 2 methods for this one. If you think back to your days with pre-calculus, and you were given a square root with a number next to it, hopefully, by the way, we should always double check. Plug in 1. Do we get 0 on the top? Yes. Do we get 0 on the bottom? Yes. This is 0 over 0? Yes. Okay, now let's do some algebraic techniques. And one of the algebraic techniques you can do is to do something called multiply by the conjugate. Which was really just the root x, not minus 1, but plus 1. It's like me saying a plus b times a minus b. Why is that helpful? Because when we expand it out, we get a squared minus b squared. And our goal right now is to try to get rid of that square root. So notice if I multiplied by the conjugate, I will now get, if I distribute the numerator, root x times root x is x, and then root x, and then I have a minus root x. This is good, this is good, this is good, because that just disappears. And then on the bottom, I'm going to ask you not to multiply this out, and hopefully you'll see why in a minute, or less. Once again, if I were to simplify the numerator, look at this. I have now x minus 1. And now, can you see why I told you not to expand out the denominator? Because yes, these 2 factors now divide each other out, and then you're left with 1 over the square root of x plus 1, and then I can plug this in. That's 1 plus 1, that's 2, done. And by the way, if you're curious, in this case, the whole is at 1 comma 1/2. Cool. Now, if you didn't like multiplying by the conjugate, you could have actually factored this one too. But I'm not going to show you. But if you are curious about factoring and how you can solve number 4, then contact me and find out. All right. Number 5. Oh, there's a little plus sign next to the 2. Have you noticed that? So this time we're actually finding a one-sided limit. Interesting. So my question is, I guess we can plug this in too. If I were to plug this in, I wouldn't be plugging in actually 2. I'd be plugging in something like a little bit more than 2, like 2.001, right? 2 from the right-hand side. And if I did that, look at what will happen. The top would be something very close to 2, like 2.0001. And the bottom would be like 2.0001 minus 2. And if you think about that, that bottom number, or the denominator, is really small. So a number like 2 divided by a number that's really small, that gives us something like, yeah, you're right, positive infinity. So you can quote that as your answer, or you can actually just say this also does not exist. Both are okay in my books. And by the way, for number 5, do we actually have a whole at 2? No, we don't. What do we actually have at 2, just for fun? Yeah, it's a vertical asymptote at x equals to 2. Cool. So really, if you think about this, this is a review of what you've learned in pre-calculus, especially when you dealt with those rational functions. All right? Cool. Now let's go on. Let's look at number 6 and then 7. If I ask you to talk about continuity, discuss the continuity of this function. What do I mean by discuss? Well, I'm really saying to you, is this function continuous? And if it is everywhere, just say that. And if it's not continuous at some point, tell me where. And tell me why it's not continuous. Well, we know that the function is true, this expression, for all values of x that are not equal to 3. And at particular value of 3, it says it's equal to 5. So really we know that this function exists, because a rational function exists and is continuous everywhere, except perhaps at x equal to 3, because that's where we have our non-permissible value here. So the question I have for us is, how do we figure this out? Well, perhaps we should look at the limit, because when we talked about continuity last day, we needed to show that if it's continuous at a point, the limit must be equal to, do you remember? The limit as x approach to a of the function must be equal to, the actual value of the function. Well, we know the value of the function, that's this. At 3, the value of the function is 5. So the question now is, if at the limit at 3, is it 5 as well? If it is, then of course it's continuous at 3, and therefore continuous everywhere. And if it's not, then therefore it's not continuous at 3, but everywhere else is continuous. So how do I figure that out? Let's calculate the limit as x approaches 3 of the function x squared minus 2x minus 3 over x minus 3. I'm going to run out of space, but I hope you will not. I'm going to factor this. Ooh, I like factoring. My favorite F word. Well, yeah, that didn't sound very good, but you get it. We'll divide each other out. We have the limit now as x approaches to 3 of x plus 1, and then, we evaluate and we get 4. Ha ha ha. So what does that mean? That means we actually have a hole, right? Because we have a hole at 3 comma 4. So if I were to actually do a quick sketch of the graph, which I didn't ask you to, but I thought it'd be nice to quickly do it. This simplifies to a nice line where the slope is equal to 1, the y-intercept is equal to 1, so something like this. And then notice at 3, yes, the y value here is 4, and it continues on. But notice, because this is a piecewise function, we have at 3 a y value equaling 5. So look at this, a hole, and then the dot that is not plugging the hole. So we call this a removable discontinuity, because I can remove this discontinuity by quickly just moving the dot and filling the hole. But we're not going to do that. So in any case now, let me just write this down. I will say, discuss the continuity of this. I'll say the function is continuous everywhere. The function is continuous everywhere except at x equal to 3. Why? I'll say because b/c, the limit as x approaches to 3 of the function does not equal to the value at 3. And in this case, what we have is, note, we have a removable discontinuity at x equal to 3. All right, so that's how we can talk about continuity for given a function. I've shown it to you visually, also algebraically, and make sure you write a nice statement out here too. Okay, number 7. Oh, this time I told you that this function g is continuous. And it's continuous everywhere. If I don't say everywhere, it's just as continuous everywhere. But the question is, what's the value of a to make this continuous everywhere? So in essence, if you think about this, we have a parabola, and we have a line. If I were to quickly draw this out, and you don't need to, by the way, I have this line x minus 3 when it's less than 2, so minus 3, so something like this. And then I have up here some, what's that going to be? Oh yeah, parabola? So some sort of parabola that's on this side. The question is, what must that value of a be so that they actually connect and actually make this a continuous function? So once again, the careful rationale, or not rationale, the careful reasoning behind this is we need to look at what particular value of x. X equals to 2. And then once again, let's find the limit as x approaches to 2, and let's make it equal to the value of 2. Now, what we need to do to make sure it's continuous at 2 is we need to figure out the limit as x approaches to 2 being equal to the value of 2. Now notice the value of 2 here also seems to be equivalent to the left-hand limit because of this less than or equal to sign. And so really, in order for us to figure out the limit here, we need to ensure that the limit from the left also equals to the limit from the right. So I think that's what we should calculate here. Now the limit from the right is just the function 3x squared plus a. And the limit from the left is just that function x minus 3. I should once again put my proper notation here. And I want you to evaluate this, so I'm plugging in 2, so I get 12 plus a, and then I get negative 1. And then I have to solve for a, so just a equals to, I believe, negative 13. And because this limit now exists and the limit equals to the function value, we are very confident that a must be equal to negative 13 in order for this function to be continuous for all values. Okay. Now we've done a lot of algebraic work, but you know you can actually use a calculator to help you find limits too. So I've given you this crazy function now. If you can bring out your calculator, boop, and I'm going to ask you to try and use a special feature on your calculator to calculate all these limits values that are close to 1. Okay, so here we go. I'm going to ask us to actually just go ahead and type in the equation first of all. Make sure you put brackets around both the numerator and the denominator. So x cubed minus 3x squared plus x plus 2. Close the bracket. There's my numerator. Do the same thing for the denominator. 2x squared minus x plus 2. Let's just double check I typed in everything correctly. I think I have. And I know you're tempted to press graph, but I would rather you press table, which is second function graph. Here we got a nice table. You're like, what's this table? Well, right now for my calculator, it actually generated some random numbers for me. It chose random values of x, and it produced the corresponding value of y. Now, if you want to actually put in the numbers, well, go to this feature called table set on top of the window button. So press second function window. And this is where if you were to change these things and just say, hey, yeah, I want this to be ask. Hey, it should have actually done it. Let's see if it works. Go to my table feature. Can I actually plug in numbers? Oh, I can. Oh, great. So yeah. As long as it says ask for the independent variable, that's like your x value, then you can type them in. And as long as dependent says auto, it will automatically fill in the dependent variable or the y variable for you. So going back to the table now, I want to actually find out these particular values. 0.9 for x. So let me go back. 0.9, 0.99, 0.999, 1.001, 1.01, 1.1. So I've actually found values that were close to 1, both from the left side, those are the 0.99s, and from the right side, that's the 1.001, and you've actually calculated the y value. So let me just write them in, and then we'll discuss what you think the limit is at x equals to 1. 5.73. Remember 3 decimal places, friends. 50.749. 500.75. Negative 499.200, I guess. Negative 49.250. And then ultimately 4238. Okay, oops. Negative 4.238. So really my question is, as you look at these values, what's going on when x approaches 1? If I were to graph this out, it looks like To the left of 1, the graph is shooting up, woo, like this. And then to the right of 1, the graph is way down here like that. So you'd be thinking, this probably looks like an asymptote. Yes, it does. So therefore, what is the limit? Yeah, it does not exist. Okay. And so now what I'd like you to do next is try for B. See if you can actually do this yourself now. So same function, plug in the values. You try this, plot the answers, predict what the limit is at x approaching 2, and then come back and check your work with mine. Go. Did you say that the limit here at x approaches to 2 of the function equals to like perhaps 0.333 or 1/3? If you did, that's great. Awesome. Now, there is one more question. Apologies, it's on the next page. But I said, can a table like these be used to find limits with absolute certainty? Think about that. Absolute certainty. And I would say not absolute certainty. I mean, this is a good way of trying to estimate and figure things out, but there could be some hidden behavior at that value, and we, I think, looked at a graph like that before where it was oscillating back and forth perhaps at the limit. So we can't know for sure that this is the actual limit, but we can get a good approximation, I guess. So I'll say, can a table like these be used to find limits with absolute certainty? The answer is no. And I say there could be some hidden behavior at the limit. Okay? All right. One more topic for this unit, and then we're done. Well, not this unit, this lesson. It's called the Intermediate Value Theorem, also commonly abbreviated with the 3 letters IVT. Okay, now, we'll be looking at a few theorems in calculus. One of them talks about the idea of an intermediate value. Intermediate means like between. Okay, so with all theorems, there are some conditions that need to be met before the theorem is valid. So if you read this statement, it says if f is continuous on AB. So that's an if, right? So a condition. Here's your first condition. F has to be continuous. Okay. And it says k is any value between f of A and f of B. So here's your second condition. You have to pick a k, which is a y value. So here we go, k. And it has to be between f of A and f of B. So it has to be between f of A, f of B. So if you have these two conditions met, then it says, so here's the conclusion of the theorem, then there is at least one x value, which we call c, and that c is between A and B such that if I find the y value at c, it's equal to k. So in essence, they're saying, look, the function's continuous. If I choose a k value that's between the lowest and highest y values, or actually it doesn't have to be just in the interval, then I know there's a c value, which is an x value, that corresponds to the chosen y value, which is k, and that c must also be between the x values of A and B. Okay? So statement 1 and 2 lead to the conclusion of this right here. Okay? So let me try to show you this with 2 examples. For number 9, I just want you to tell me, does the intermediate value theorem guarantee a c value on the interval? So really what I'm saying is, does it actually hold true for the 2 conditions that I've highlighted in yellow? So your first condition is it continuous on the interval? So for part A here, I'll say condition number 1, yeah, that's met because f of x is continuous. It's a parabola on the interval 0, 5. That works. Ding! And then we have to show that the k value is between f of a and f of b. Now the k value in this case is actually 12. So now I have to show that it's in between f of a and f of b. So let's evaluate f of a. F of 0, of course, is just 0 squared minus 0. F of 5 would be, what, 5 squared minus 5? That's 20. So yes, okay, yes. So the k value, which is 12, is definitely between f of a, which is 0, and f of b, which is 20. So that holds. So because that holds, therefore I can say, yes, by the intermediate value theorem, this guarantees a c value in the interval from 0 to 5 such that f of c equals to 12. So I can actually go ahead and find this value of c. Okay? But I'm not going to do that yet. Let's do b now. So once again, you got to think to yourself, does this expression satisfy the two conditions? And I can say to you, yeah, this is a rational function, so it's continuous everywhere except perhaps at 2. Uh-oh. Look at my interval. It's from 0 to 3, and look where my... Oh, that hole? Where is that hole? Yeah, it's at x equals to 2. Oh, no. So for part B, I already know that statement number 1 does not hold. So g of x is not continuous in the interval from 0 to 3. And therefore, the intermediate value theorem does not apply. Okay. Now, I'm not saying we can't find a value, but I'm just saying we can't use the intermediate value theorem to prove that it works because the function is not continuous in the interval that you've chosen. Now, if I change the interval, like, from 3 to 10, that would be okay because in that interval, this function is continuous. But in the interval of 0 to 3, it's not. Okay, so number 10 says, hey, let's go back to example 9a. We said that we should be able to find the value c, so let's go ahead and find it. So remember, the idea is the value of c must be equal to k. So the k value is 12, and f of c would just be me taking the function f of x and replacing x with c. Here's the function f of x. So let's replace it with c, so it becomes c squared minus c. I'm going to move all the terms to one side now. C squared minus c minus 12 equals to 0. Then you can factor c, c plus 3, c minus 4. And then we find the answers of c equals to negative 3 and c equals to 4. And if you left your answer like this, I'd be like, whoa, double check. Remember, I'm only looking at values of c where? In this particular interval. What interval I'm looking for? Between 0 and 5. So which one works? Yeah, c equals to 4. Which one do I have to discount here? That's right, c equals to negative 3. So remember, c equals to 4 is the value in the interval that I'm looking at from 0 to 5. Okay? Woo! That's it.